So it's my pleasure to have Maxime to be our fifth speaker this morning graduate speakers, and he will be speaking about parameterized invariant manifold and applications in celestial mechanics. Please, Maxime.
Okay, hello everybody. Thanks for the organizer for the invitation, and thanks for everyone for coming. My topic is about parameterized invariant manifold and their application in celestial mechanics. The manifold approach that I'm going to be using is not new, but I'm going to still recall it as it is. So what I'm going to be using is the parameterization method. The goal of the parameterization method is summarized in this picture. What we want is use the knowledge of the linearized system and what happens using Floquetian knowledge of Floquet exponent, and find a parameterization P that will map those trajectories that we know into the phase space that we don't know, and so that we can compute trajectories using something simpler. This conjugacy relation is equivalent to this problem here. What we want to do is find a solution P function that is solving this PDE. This PDE is representing what P needs to satisfy, and we have two conditions. The first condition is that our function P, the image is centered around the periodic orbit gamma, and that the derivative are equal to the tangent bundle, meaning that the function we're looking for is tangent to the stable space in the case, or unstable space in the other case. Here I have two assumptions in my presentation that will not be a problem in my example of interest. The first one is that my bundles are orientable and therefore have the same period as the orbit, and that my eigenvalues or Floquet multiplier are not resonant, so that I can, for simplicity, assume that my parameterization will be expandable with a Taylor expansion. Okay, so here's a sketch of how I want to validate this computation of P. So what I want to do is not new. It's to compute the function Taylor coefficient by Taylor coefficient. And we write the problem using a fixed point argument, Rayleigh polynomial or Newton-Kantorovich type argument. So what we want to do is compute the coefficient all the way up until 0 is a good approximation from the remaining coefficient. Validate the non-zero one by one using a fixed point argument for each of them, and then use a uniform argument to show that all the other zeros are good enough approximation. Okay, this is also something that was done in previous work. What we want to do that's novel is use the structure of the Fourier space as well as the knowledge of the periodic orbit to improve our validation and to make it a little bit more accurate. Okay, so using a Taylor expansion for P, resolve into solving this system of ODEs for alpha. So here what we have is get a vector field capital F that generates our ODE. We evaluate that at P, and we look at the alpha coefficient for the Taylor approximation. So we do a matching power on both sides, and we get this equation here. Here, this is the scalar product, alpha times lambda, which is all alpha 1 times lambda 1 plus alpha 2 times lambda 2, and so on. Okay, and then we want to solve this for all alpha. We have already that some information is given by our condition. The two first order of coefficient are given by my condition. The first one is that it's the periodic orbit. The other ones are given by my bundle. So I can solve those the usual way, find my periodic orbit, find my tangent bundle, parameterize them, find a rigorous error on them. And then for the other ones, I will be solving a slightly rewritten form of this equation where we break down the right-hand side into two pieces. One piece that will be involving strictly A alpha, the current coefficient that we're trying to solve for, another piece that depends only on the lower order coefficient. So what we notice that this can be done pretty straightforward when F is polynomial, for example, and then we can just take away two pieces out of the Cauchy product that would be an outcome of my product in my polynomial. Okay, and then again, this again starts to allow us to parallelize all the proofs and to reuse some information that we already computed when we do the validation of my finite order coefficient. And then we can validate some coefficient up to a finite order. And then we can rescale, when the proof stops, we can rescale the manifold so that the validation is good enough and taking care of error spreading. And we want to see that 0 will be a good enough approximation for the remaining ones. Okay, now what we do from there is that we're going to try to rewrite this problem into a fixed point problem for A alpha. Okay, so what we're going to first do is rearrange everything so that all the coefficients involving A alpha are on the left-hand side, and the right-hand side is independent of the A alpha that we're currently solving for. And what we want to do is notice that if we're able to invert this piece here, we would be able to have A alpha as a fixed point of my remainder that I applied the inverse of this operator to in order to find my A alpha. But what you might notice is that, unfortunately, this is not bounded, and we have to hit something with a preconditioner so that I can find an inverse for all alpha. Okay, so what we're going to do is try to switch to Fourier space and use extra knowledge of the periodic orbit. So let's switch to Fourier space and rewrite our notation. So when I did my validation for the periodic orbit, I defined some operator f calligraphic such that my Fourier coefficient, lowercase a sub 0 of my periodic orbit satisfy f of a0 equals 0. When I take the derivative of this operator and then use it to rewrite my previous equation, I get something that looks like this. Here I have my remainder now in Fourier space. The identity here comes from the fact that the Fourier operator is fully diagonal in this piece with respect to derivative and respect to this addition. And the derivative is absorbed by, the derivative with respect to time in the first operator is absorbed by this object here. And now what we want to know is work on this operator in Fourier space. So what we're going to do is recall some useful knowledge from the validation of the periodic orbit. Thankfully, I'm just after Gabriel, who spoke about the Rayleigh polynomial or Newton-Kantorovich approach, so I can skim over the detail a bit. What we have is a dagger and approximate of this derivative, not at the exact coefficient, but at my approximation. And then I have an approximation of this inverse that I have, okay? More specifically, what I have is that when I do my validation, I compute those three bounds. So I have Z0, Z1, Z2 of R naught that are three constant, and assuming that the proof succeed, those three constant add up to something that's smaller than 1. And I also have this inequality that stands in the case where my proof succeeds. And what is this? This is a soup over the ball. And I know that if the proof succeed, my true coefficient are inside that ball so that this soup is bigger than this specific term at my exact solution A0. And what that allows me is to look at the operator that I don't know in my previous operator, hit it by A, and then rearrange that by adding and subtracting some terms so that I have the identity minus something that I have full control over. What is the full control that I have? Well, I know that minus E is bounded and normed by Z0 plus Z1 plus Z2 of R naught, okay? And now what I want to do is introduce this piece. So I hit my equation with A on both sides. So I have the same equation as I had, but now I have A. And I didn't change my solution. I didn't introduce any problem because A is assumed to be 1-to-1 thanks to the fact that the validation worked. Okay, and now what I want to do is work on my new operator and justify that this will now be invertible. Okay, so what we do is we define L alpha to be the left-hand side that is the operator that's hitting my A sub alpha. I want to find that it's invertible, and then I will be able to use a fixed point argument with my inverse here, given that my A, which is my full series of Taylor coefficient, when I evaluate this and I evaluate the remainder at alpha, and then I hit it with L alpha inverse, I get my alpha as a fixed point of this. Okay, so now how can I argue that this is invertible? This is, again, something that's going to be involving my knowledge of the previous proof. So let's rewrite L alpha. L alpha is exactly that. I already have an expression for this thing. I have that this is the identity minus E. And at this point, what I can do is regroup the two pieces that are fully known, the identity, and my A, which is my approximate derivative, which is only non-diagonal in the finite piece. So I can factor it out, assuming that this is going to be invertible. And I get M alpha, which is identity minus my scalar product times A. And then the identity minus something over that I will have control of on both the norm. So I can potentially apply a Neumann argument over this piece here. Okay, so why is it that M alpha is invertible? Well, again, as I said, this is only non-diagonal on finitely many terms. I can rigorously validate that this is invertible and find a bound on the inverse using interval arithmetic and some by hand estimates. Okay, so I'm able to find a bound on the inverse. I make this bound uniform so that it doesn't depend on alpha, and that I have that whenever my bound multiplies to something smaller than 1 when I multiply with the bound on E, I have that my Neumann argument will stand and I will be able to invert L alpha. Okay, so now I have an algorithm that tells me if I am able to compute this bound B n sub t, and I have the success of my validation of my periodic orbit, I am able to invert L alpha, and I am able to use a fixed point argument to prove that 0 is a good approximation for all my remaining coefficients. Here are some final remarks on that. We can note that the error bound, as I mentioned earlier, when I prove my finite coefficients that are non-zero, will increase, but this can be offset by rescaling my manifold. The bound B and T will decrease when my Taylor approximation that I projected increase in dimension. And why is that? It's that to compute the bound, what we did is that we used the fact that if alpha goes to infinity, alpha times lambda will go to infinity as well, so that 1 over this will go to 0, and that I am able to find a bound that depends uniformly on Z, and Z will be included in the bounded region. And you can notice that this region will shrink if I increase n sub t. And therefore, I will have a smaller bound. Okay, so that being said, now what I want to do is use those manifolds, find some rigorous validation, and use them in application. I will have an application with 1 eigenvalue, an application with 2 eigenvalues, and this application will both be to find homoclinic and heteroclinic connection in celestial mechanics. Okay, so let's recall what is a connecting orbit as a boundary value problem. So we know that regardless of how big the image of my two manifolds is, this boundary value problem allows me to take care of the asymptotic dynamic for my homoclinic or heteroclinic connection by assuming that I start and finish in my unstable and stable manifold. And then I only need to know my connection as a solution of my ODE on a finite amount of time. This can be done using either Chebyshev polynomials interpolation or directly a Taylor integrator. So we approximate that in a couple of examples. We computed some homoclinic connection. Here's one first example that gathered my interest. Is the Hill's four-body problem. This problem was introduced in a paper by Jaime Burgos Garcia and Marian Guedia. And what they did is that they took the idea of the Hill's approximation and applied that to the four-body problem so that they can study the behavior of this problem nearby a Trojan asteroid. So what they want to do is introduce a symplectic rescaling that depends on the mass ratio of the fourth mass, and that will just change the Hill's body problem by some factor here that depends on the eigenvalue of your rotating transformation. Okay, so what we want to do is see that, well, at 0, we got the Hill's regular problem, and we want to see if all what we know in the Hill's regular problem continuates into the new problem that's introduced here. So what we did is we found this pretty regular, conventional, and well-known connecting orbit between two halo orbit around the fourth body. And what we would have is a rigorously validated connecting orbit. You can notice that the two manifolds look very small, but indeed we were still able to take care of the asymptotic behavior because of my previous remark. And this has been rigorously validated. I don't have the numbers because that takes too much room in a slide and it's a very short talk. But what we have is that this is at mu equals 0 and energy equals 4. And we were able to continuate this solution into the Hill's four-body problem for the mass ratio covered by the Trojan asteroids, which are the object of interest in the paper that I mentioned. So this is an example where the manifold are two-dimensional, so one periodic dimension and one eigenvalues. I have an example where the manifold is three-dimensional, so two eigenvalues. It is in the full spatial three-body problem. So I have a periodic orbit around L4, which is the Lagrange point a little bit above the x-axis in the problem. And I found this unstable and stable manifold, and then I computed a homoclinic connection to this orbit in the full spatial problem. And here what you see is displayed in X, Y, and Z component. The red and green parts are covered by the dynamics that we know on this manifolds, and the blue part is known from the Taylor and Chebyshev integration. So this is the two applications that I've covered so far. Obviously, this was covered in the case of ODE, but we are pretty confident that this approach would work in other systems where there is only finitely many multiplier eigenvalues of interest. We use the fact that Fourier is diagonal in detail so that we can use the structure, but we are interested in looking at other bases in the future, and then we can find other constraining of connecting orbit in other problems. That's pretty much all I had to say for today, and here's some further reading, and thanks everybody for listening.
Thank you. Thank you, Maxime. Are there any questions or comments?
Maybe a quick question about the end. You said that the manifolds, they were quite small. So
Yeah.
Is it just because you don't need them to be larger, or is it because it was really hard to get them larger?
Okay, so in the case that I'm interested, the vector field is fourth or fifth order. And because of that, the numerical error spreads really fast as I go up in Taylor mode. And I have to rescale by a lot for the proof to work. So in terms of estimate of AU, like, so 1 being the unit in that system, I'm like at 10 to the negative 6, which is not large if you look at this system, but if you look at the real life application, it's actually quite considerable, despite despite the big rescaling.
I see. Thank you.
Thanks.
Other questions, comments?
I may ask a question. So you said in your future, your outlook to the future, maybe it wasn't the previous page, you said that that can be extended to other cases with finitely many stable, unstable eigenvalues. Is that, would you have to have that information of finitely many stable or unstable eigenvalues in advance, or would that be a part of which you can prove that there are only many stable, finitely many?
This is not something I will be able to prove. I have to know beforehand that there is only finitely many. So it would have to be a beforehand proof that there are finitely many of interest and that they are non-resonant, and then I can proceed to my validation.
But that proof could be computer assisted.
Yeah, exactly. That could be another computer-assisted proof.
But that would have to be completely independent of your approach, right? That's an independent story, so to say.
Yes.
Yes. Okay, I understand. Thank you.
Thanks. Thanks for the question.
Other questions? Actually, I just have one. So in the boundary value problem, you mentioned Chebyshev or Taylor. Do you use both, or you use like only Chebyshev or only Taylor?
So I use Chebyshev to find my approximation, and then we do it in Taylor to prove.
And why?
Because the Chebyshev, the norm of the inverse, when I try to validate it, is too big, and then my validation fails because of that. My Y bound gets blown up considerably by the norm of the inverse.
And do you know, did you investigate? It's kind of surprising. It's the first time I hear that Taylor is fundamentally kind of better than Chebyshev for some BVP.
In that case, Taylor is possible because the integrating time is not so long. But I assume that for longer connection, we will have to figure out how to make Chebyshev works, and then we can do the validation.
And did you explore like the theory of that? Because that's kind of an interesting
I haven't explored too much yet, but that's definitely something I'll do in the future.
Yeah, it's kind of surprising. Okay, thank you.
We tried domain decomposition, and it didn't really improve the problem.
Okay.
For example.
Yeah, it's kind of fascinating. Yeah, surprising. Okay, very good. I think we're out of time for now. So let's thank Maxime again. Thank you very much, Maxime.